Welcome back to History of Mathematics. We're continuing our work in Chapter 4 of our textbook, concerned with Archimedes and the later Hellenistic period. Now, one of the names mentioned in this chapter is Eratosthenes, and Hollingdale mentions him as a correspondent of Archimedes, whom they discussed Archimedes' method, the method of exhaustion, basically. So I'd like to talk a little bit about Eratosthenes. He was the librarian and eventual head of the museum at Alexandria. Now, as we've discussed before, the museum was actually more what would be called a university nowadays. And he was essentially a polymath. In other words, he was versed in diverse areas: poetry, literary criticism, mathematics as well. And today he's best known for a couple of things, one of which is his computation of the circumference of the Earth. So I'd like to discuss how Eratosthenes was able to get a fairly accurate approximation for the circumference of the Earth back then. So, a couple of things Eratosthenes knew. Eratosthenes knew that the city of Alexandria was 500 miles north of the city of Syene. These are both cities in North Africa. Eratosthenes also knew that during the summer solstice, there was a well in that city of Syene where at noon the sun would shine directly down to the bottom of that well. You wouldn't have the side of the well in shadow shining straight down there. And he also knew that in Alexandria, the noonday sun made an angle of 7.5 degrees with the vertical. It's actually not too difficult to measure the angle of the sun using some elementary tools. In fact, you could do it yourself with a protractor and a weight and a string. Okay, so Eratosthenes knew that the angle that the noonday sun made in Alexandria was 7.5 degrees. So let's go to this picture here. The point I've got labeled A right here represents the city of Alexandria. The point I've got labeled S represents the city of Syene. This angle right here is 7.5 degrees. E represents the center of the Earth. Now we're going to assume that these lines L1 and L2 are parallel. Okay, so these lines represent sunlight. Now the sun is so far away that it's not that bad of an assumption to say that these lines are parallel. Now, Eratosthenes knew that in the city of Syene, the noonday sun shone directly down the well, so the line L1 through S to E, that's a straight line right there. So this sunbeam is shining straight down on the city of Syene, and this sunbeam, which is parallel, is making an angle of 7.5 degrees with the vertical, right? From the perspective of Alexandria, this right here, that's the vertical line, okay? And the sun is making an angle of 7.5 degrees there. So let's do some calculations here, similar to what Eratosthenes would have done. Firstly, we would review the facts that vertical angles are equal. So this angle is 7.5 degrees, that means this angle is 7.5 degrees. And we also know that alternate interior angles are equal. So 7.5 degrees, 7.5 degrees, 7.5 degrees. Now the arc from A to S, that's 500 miles. Okay, Eratosthenes knew the distance between these cities. And we just figured out that this central angle AES was 7.5 degrees. So if C represents the circumference of the Earth, then if I take this 500-mile arc over the whole circumference, that should be the same as the ratio of 7.5 to 360, right? Because this is the angle that we've subtended, and this is going the full way around. If you solve this for C, you get approximately 24,000 miles right there. Okay, so Eratosthenes got an estimate for the circumference of the Earth using some elementary geometry. Now, this figure of 24,000 miles is actually fairly close to estimates made using more sophisticated modern methods. So it's kind of a very elegant argument for getting this information that Eratosthenes was able to produce.